Waves, an animation short on derivatives and integrals. Functions can be graphed as dependent variables in terms of independent variables. Independent variables are the input of a function, which transforms independent variables, and create an output, a dependent variable. We can graph two functions which represent the horizontal and vertical movement of a point of interest on the red blade by continuously plotting the x and y position as the blade rotates. The independent variable of these functions is theta, which measure the angle between the current position and the original position of the blade. The dependent variables of these functions are x and y, which measure the one-dimensional distance between the current position and the original position of the point of interest. These are the sine and cosine functions. The sine function plots the vertical position of the point of interest, and the cosine function plots the horizontal position of the point of interest. The derivative is the instantaneous rate of change, or slope, of a function at a point of interest. We'll call this point P. We can approximate this slope by finding the rise over run of a secant line that passes through P at an arbitrary point Q. Note that our initial approximation of slope is 0.387, or 21.15 degrees from horizontal. As point Q approaches point P, the approximation becomes more and more accurate. If we make point Q infinitely close to point P, the secant line touches only a single point on the function and becomes a tangent line. The slope of the tangent line gives us an exact value of the instantaneous rate of change at the single point P, our derivative. Note that our initial approximation of the slope at point P was 21.15 degrees, and our final exact value for the slope was 30 degrees. It makes a huge difference to use 2 points that are infinitely close together, or effectively the same point, which has a distance of 0 from itself. The tangent line to the sine function starts out with a steep slope, which means that the y position of the tip of the blade is changing rapidly. The closer the tangent line is to the apex of the sine function, the shallower the slope. This makes sense, because the vertical position of the tip of the blade changes very rapidly when the blade is nearly horizontal, and very slowly when the blade is nearly vertical. The initial rate of change of the sine function is 1, because the slope is measured as rise over run, and 1 over 1 is equal to 1. We can say that the blade is instantaneously rotating vertically by 1 unit and horizontally by 1 unit. This slope, represented as an angle, is 45 degrees. Sine and cosine have a very special relationship. If we examine the cosine function at theta equals 0 degrees on the horizontal axis, we find that the value of x on the vertical axis is 1. If we examine the sine function at theta equals 0 degrees on the horizontal axis, we find that the value of y on the vertical axis is 0. No surprise there, because a perfectly horizontal blade means that the tip of the blade is 1 horizontal blade length from the center of the propeller, and 0 vertical blade lengths from the same center. The magic happens when we examine the slope, or derivative, of the sine function at theta equals 0 degrees on the horizontal axis. It's 1. The same value as the output of cosine function at theta equals 0. If we examine the cosine function at 90 degrees, we see that the value of x on the vertical axis is 0. If we examine the sine function at 90 degrees, we see that the value of slope m is also 0. Comparing these two functions side by side, we observe a continuous correlation between the value of cosine theta and the value of the derivative, our slope m, of sine theta. From this we can infer that the cosine theta is the derivative of sine theta, or quite literally, that cosine theta is derived from the value of the instantaneous rate of change of the function sine theta. Integrals. Integrals are defined as the area under a function. It is important to note that by under, we mean the area between the function and the x-axis. To find the area under this function, we must first define a beginning and end point, or an interval on the x-axis. In this case, the interval is from 0 to 360 degrees. We can approximate the area under the curve and between our set interval by drawing many rectangles of equal width and placing them within the function so that either the left or right corners of the rectangles touch the tip of our function. If we draw a parallel to derivatives, we can think of the corner that touches the function as point P, our point of interest, and the horizontally adjacent corner as our arbitrary point Q. A shortcoming of this method of approximation is that some of our rectangles will have part of their area outside our function boundaries, and others leave areas inside the boundaries of the function unfilled. Another shortcoming of this method of approximation is that the wider our rectangles are, or the distance between P and Q, the greater the difference will be of our approximated area and the true or exact area. This is the same situation we saw with the derivatives, and the way we solved that problem was to make the distance between P and Q infinitely small. If we apply the same principle to integrals, we see that the rectangles of an infinitely small width will fill the area under the function perfectly, with no portion of any of them spilling over the boundary of the function or leaving areas within the boundary of the function unfilled. There is another special relationship between sine and cosine functions. If we sum up, or quite literally integrate, all of the tiny rectangles to any given point on the x-axis, we see that the integral, or area, is equal to the value of sine theta, which gives us a y position for our point of interest on the propeller. This means that derivatives and integrals are inverse processes that undo one another. This is why they are sometimes referred to as the derivative and antiderivative.